was supposed to chair the last talk, and I was also supposed to chair the 9 o'clock today morning talk, which I came late. But I have an excuse. In fact, this is the first time I'm chairing anything ever, so I just didn't remember. And also for the last talk, I guess I wouldn't want to be naughty chair. Maybe I would be follower, but not chair. So this talk is by Karl Wimmer. He will talk about agnostic learning.
All right, thank you. So we're going to talk about agnostic learning. There's going to be a special focus on agnostic learning of linear threshold functions and functions of linear threshold functions. The big difference between this talk and Adam's talk from yesterday is that we're going to focus on finite domains, so either the Boolean cube or subsets of the Boolean cube. And so let's talk about the whole Boolean cube case first. This is just a standard definition of a linear threshold function, which we might abbreviate to LTF. Just says that if you put a plus or a minus on each vertex of the hypercube, you could draw a nice geometric plane that separates them. This is probably the most wordy definition I have in here, so we'll start with that. This is just a definition of agnostic learning, which, like Adam, I don't want to spend a whole lot of time on. Sort of the concise idea is that we want to be epsilon competitive with some function class. So we say that a function class C is agnostically learnable with respect to a distribution D if we can output some hypothesis H such that for an unknown target function T, which we have access to through labeled random examples, that the error of what we output is at most, well, it's only epsilon worse than what the best thing in C would be. So we're just trying to be competitive with what C would do. So if there's something good in C, we have to do something good. If there's no good function in C, then our algorithm can just output whatever. There's really no requirement here. So some of the background, Cliven's, O'Donnell's video showed that if you've got the intersection of KLTFs, you can learn them in polynomial time for constant k and constant epsilon. And this is for the uniform distribution on the Boolean cube. The algorithm is just a low degree algorithm, which has been around for a while. It's essentially just solve a least squares problem, and you're looking for a low degree polynomial up to some bounded degree, and this is where the exponent comes from. And your hypothesis is just the sign of the polynomial. So it's fairly straightforward. The algorithm's been around for a while. They essentially show that this algorithm works for learning this class. If you want agnostic learning, we have to wait a few years for Cliven's Mansur video to show that we can do agnostic learning, the same class. And really the big idea here is to do L1 regression instead of L2 regression. Of course, to do this, we usually use an L2 regression guarantee anyway, but the L1 regression actually gives you agnostic learning. And while this result is for the uniform distribution, you can really plug it into whatever distribution setting that you want, as long as you have a nice low degree approximator. And again, up to some small factors here, we're going to output the sign of P. And so the proof here relies on the noise sensitivity method. This is how we get things like functions of KLTFs. A little bit more background. If we're in the Boolean cube, the influence is defined as just the probability that if we flip the ith coordinate of a string, that this changes the value of the function. We won't actually use this measure too often. We're going to use a related measure, the noise sensitivity. The noise sensitivity is the probability that we change the function if we start from x and take what we'll call a delta noisy copy of x. The n here should probably really be bold too, because it's sort of a probability experiment. We start with some random string, which we might have here. How do we draw n of delta? Well, we're going to independently mark each coordinate frozen with probability 1 minus delta. And so we might get something like this. And then anything that's unfrozen just gets re-randomized. And so then we get other things that are re-randomized, so maybe we get something else, maybe we don't. The key fact here is this kind of ugly looking expression. You don't really need to know all of the specifics of it. You don't even really need to know much about the Fourier analysis that's going on here, just that these Fourier coefficients are the coefficients of f. If you wrote f out as a multilinear polynomial, if you think of f as an LTF, it's the sign of a degree 1 polynomial, but it can be a very large degree polynomial when you write it out in this form. The big idea here is that the sum of squares of the coefficients is 1, and these multipliers on the noise sensitivity here are going very close to 1/2 as you increase the degree. The size of S here is the degree of the related monomial. So as you increase the degree, you're approaching 1/2 very, very quickly. So this is actually going to be the key idea that we're going to want later. That's why we've got the nice colors here, so we'll refer to them later. And then the chain goes that if you have low noise sensitivity, this is really what the noise sensitivity method does. Once you have this, then there's a long chain of implications, and if we go through KKMS, we get agnostic. Right? Any questions so far? This is just all background, nothing new. All right, and so to start the chain off, we can use Perez's theorem, such that if f is an LTF, then the noise sensitivity is bounded at parameter delta. The noise sensitivity is at most square root delta. And by a union bound, if you have a function of k LTFs, then you can also bound the noise sensitivity. You can just union bound. And to get this exponent here, we set this up so that the right-hand side is epsilon squared, and this is what KKMS needs to guarantee that we really get agnostic learning with a good approximator in L1. And a paper in 2008, this actually works in product distributions too in a very general sense. But we really don't know how to do anything much more than product distributions. Especially in the Boolean cube case, we saw Adam's talk on log concave distributions, but if we're talking about distributions over the cube, we don't really know how to get too far away from product distributions, or things that are essentially very close to product distributions. So this work is going to extend this to permutation invariant distributions, which was in the title. And so these are just distributions where the distribution, if you condition on any Hamming weight, the distribution becomes uniform. Equivalently, the probability mass on any string remains the same if you permute the string. So you have a string of minus ones and ones, you permute the minus ones and ones, the probability mass doesn't change. In the Boolean hypercube case, a distribution is permutation invariant if it's just a mixture of these uniform distributions. So although it seems like we're talking about something very general, there's really sort of only n+1 degrees of freedom. It's good to note that these distributions aren't even pairwise independent. So we are really sacrificing lots of independence here. And in fact, instead of talking about n+1 different problems, we're going to unify this actually into just one problem. We're going to just focus on the case where we learn over the symmetric group. Now I think these slices are interesting because there's lots of interesting problems that you can do. Why would you look at this? Well, how I got started on this mostly was on the KL theorem over this distribution, which I proved with Ryan back in 2009. And as an application of this, you can optimally weak-learn monotone functions, which settle the long open question of Avram Blum and others. In related work, because I've actually been explicitly asked this question multiple times, I put it on here. You can also do Friedgut's-Hunte theorem in this domain. This is an unpublished work of myself. So if you were thinking about that from KKL theorem, I can kind of tell you how to do this. And like this talk is going to use some representation theory. All right, so now let's get into how we're actually going to set some of this stuff up. We're going to go from functions over a slice to functions over the symmetric group. And so what are we going to do? Well, for any time we see a string of minus ones and ones, we're going to convert it into a permutation in a very natural way. All of the ones are going to get randomly assigned something from 1 through k. And so that is a permutation so that each of the k1s gets something different, 1, 2, up through k. And then all of the minus ones randomly get something from k plus 1 up to n. So this is how we're going to do this conversion. Now, I guess if we're going this way, it would be a many to one mapping where the many is the same always. So if you go the other way, it's 1 to k factorial n minus k factorial. So you get the uniform distribution over the symmetric group. So really, we're just focusing down to uniform distribution over the symmetric group. We want to learn some functions in this space. And so here's our roadmap using the same colors for things that we had before. And if we have time, we will go through all three of these things. If we can do these three things, then we will have agnostic learning in this case. So we're going to define what we mean by noise sensitivity, and we'll get a nice Fourier representation. We'll show that the property that we need, that the distance from 1/2 of these multipliers here in the expression we get, decay exponentially, and this is sort of why we get low degree approximators. It's not too hard to show this, but I'm sweeping this under the rug for now. And then we'll also bound the noise sensitivity for LTF specifically here, which will follow for functions of LTFs in this more general. So we're going to talk about representation theory basics. If representation theory scares you, I'm going to assume you know nothing. And I have these rows up here. They're only going to be around for like 6 slides. Then you will never see them again. So you don't need to worry about them too much. A representation is just going to be a map from the symmetric group to square matrices that preserves the algebraic structure of the group. So representation just really represents the group. Call the size of the matrix here the degree of the representation. And we're going to sort of worry, we don't really, a lot of these representations can be reduced, so we're going to consider reducible representations where you can't like funnily map them to something where it decomposes into two smaller representations. And you don't need to necessarily know you're here, but we can actually get a complete set of irreducible representations, and this contains all of the information about the symmetric group. And you don't actually have to know anything about how you would actually construct these, but just the fact that it exists. We only need it in the analysis. We don't actually need it in any of the algorithms that we use. And so if we're trying to get a basis for functions over the symmetric group, each representation contributes degree squared many functions. If we look at just the function to the reals, where we go from the symmetric group to any entry of the matrix. And so if we look at all the representations and take all of these matrix entries, then we really get an orthogonal basis for the vector space of all these functions. So we get some very natural Fourier formulas. If you want to talk about the Fourier coefficients, which in this case are matrices, you can compute them in a very natural way. To reconstruct f from its Fourier transform looks kind of bad, but it's actually not too bad, because this is just a trace of a transpose of a matrix times another matrix. So you really can think about this as expanding these square matrices out to vectors of length n squared, and then just taking their dot product. And so if you really went through the effort of rewriting it, which is conceptually easier but hard to kind of write, you could just do it as the sum of degree times a bunch of Fourier coefficients squared, or a bunch of Fourier coefficients times rho, rather. And Parseval here is pretty much the same like we had before, except that we get this annoying degree term in here. It's actually not going to be too annoying, but it is going to be along for the ride in many of our applications here. Whenever you see a matrix norm here, it's going to be the Frobenius norm, which is just the sum of the squares, which, for what we're talking about, this is really about the easiest thing you can hope for anyway. Now, fantastic, we're talking about the symmetric group, and so the irreducible representations can be indexed by partitions of n. So by partition of n, I mean we're going to take n, break it up into a sum of non-negative integer, of positive integers rather. We write them non-decreasing. This is what we call partitions of n, and so we're going to get rid of the rows often and just talk about representations being indexed by their partition instead. You can visualize these as Young diagrams. If you're playing Tetris with this set, you probably do very well. If you have, this is for n equals 4, we get all of these permutations here, or partitions rather, there are 5 of them. We just take each part, and for each part we give it a row, and each row we put that number of blocks. These are Young diagrams. And we need to talk about standard Young tableau. This really just looks like I took these and fill in a bunch of numbers, but I did it in a structured way. These things increase from left to right and from top to bottom. And we have the numbers 1 through n, each put in exactly once. Now, why am I telling you all of this? There's actually a nice fact that if we count the number of standard Young tableau, this tells you the degree of the corresponding representation. And just so that, to check that this really does work out, the degrees here, we have 1, 3, 2, 3, 1. And so the sum of squares of these things is 24, which is 4 factorial, which is really what we would expect just by a dimension argument. So everything really here is working out just like we expect. Also, the Young tableau tells you how a polynomial over the symmetric group looks like in terms of its degree. What do I mean by a polynomial over the symmetric group? I really mean a polynomial over a bunch of indicator variables that are 0 and 1 for the event that sigma maps I to j. Anytime you really see symmetric group here, you can change it into something in a subset of the Boolean cube in n squared dimensions, where you just turn a permutation into its permutation matrix and then just bust it out into an n squared length vector. The degree here is just the number of blocks not in the first row, so we get constant function over here, degree 0. Linear functions are up in the upper left corner. This guy here is the only degree 3 thing here, and it's actually the sign of the permutation function. That's +1 for even, -1 for odd. So now let's get away from these Young tableau here. Let's move on to talking about noise sensitivity so we can actually get going on our roadmap here. So the influence of a set is just the probability that if we shuffle the coordinates in S, that this changes the value of the function. You might think about this as like the variance of the set S with respect to this function f. So if we have 3, 5, 6, we'll get some of the coordinates, but we're going to then randomize over everything that's left for coordinates 3, 5, and 6. There's a nice expression for these in terms of weighting the Fourier coefficients, the degree here along for the ride. Sum of squares gets in here. We're going to actually have to average these. If you try to do any specific one of these, the formula becomes very terrible, but the average is nice. This expression here with the slash k is the number of Young tableaux that start with 1 through k in the first row. Again, this isn't obvious at all, but this does take some non-trivial work to get this expression. And again, for now, you don't really need to know where this comes from. This is just that. If you're talking about sets of size 2, then you're really talking about transpositions. And a lot of the stuff that we've done here is sort of implicit in the work of Percy Diaconis from 1989, because you're talking about just changing permutations in this method. So we're going to do something that maybe is a little bit non-standard. We'll define the noise sensitivity this way, which is very similar to what we did before. Mark each coordinate frozen with probability 1 minus delta. And so we'll freeze them here. And then we're going to usually uniformly shuffle everything unfrozen. 3, 8, 1 left, and so we'll replace it maybe with 1, 3, 8. Uniform shuffle. Now if we want to get an expression for this, let's pick the number of unfrozen coordinates first and see what happens. Well, then it really becomes just the influence of a set. And so the noise sensitivity is really just sort of the expected influence of a set. K here then is drawn as a binomial because we're taking each of these coordinates to be unfrozen. All right, so then the noise sensitivity is the expectation of this, and the first thing in our roadmap then is this expression for the noise sensitivity. Again, we get sort of Parseval's identity down here. For the noise sensitivity, we have an extra multiplier in here, which we're writing as 1/2 minus something else. And so we're going to hope that this thing gets very small very fast. Question?
Is there any sense of thinking about instead of
So adjacent transpositions, yes, but the formulas become kind of messy, actually. So it becomes a little bit different. You don't actually get, I think you don't even actually get nice things where you have the formula that looks like this. You wind up with like cross terms and maybe even some negative terms and some things that actually become kind of messy, I think. I wasn't brave enough to do that. Any other questions? And so we're going to analyze this. So we're done with step 1. So step 2, we're going to analyze this quantity over here and show that it's going to exponentially decay. We're talking about this ratio here. And so we're going to steal something from Okunkov and Olshansky from 96. One's a Fields medalist, so it's great when you can steal from a Fields medalist. We have this expression here, which say is handy. Maybe you don't think it's quite so handy. But it allows you to prove this theorem. And I'm calling this a theorem, and I'm contributing it to myself because I prove it in the paper. Everybody I asked was not aware of this. It seems very simple. So if you have like a reference for this, please let me know so I don't go around claiming this because it belongs to somebody else. That, as you make things, this is the dominance ordering on partitions, which I'll give a picture here for n equals 6. That, as you make the partition wider, and when you're looking at the Young diagram, then this ratio goes up, which kind of makes sense intuitively. As you move things down and make the partition taller, then you're making this quantity smaller. And so remember, in terms of noise here, we get the minimum noise as we get things that are wide. We get maximum noise as we get things that are tall. So again, this dominance ordering is just that if we look at all of the partial sums of the partitions, starting from the first entry and moving forward, that the partial sums for lambda are greater than or equal to the partial sums for beta.
blocks in the first row?
We don't even have k blocks in the first row. We take this to be 0. So this is maybe kind of a non-standard definition because you can talk about these things using skew tableau. And if you did this as like a set theoretic difference, maybe you wouldn't want this to be 0. But for us, we're going to take this to be 0. It's a good question. Questions? Now the proof sketch is by induction. You don't have to do this for very many exotic partitions. You can actually just worry about this case by a whole bunch of induction and using the formula we saw before. You can handle this. It's not too terribly hard to do, and it's not too instructive to see. And so this really confirms that the tall partitions are noisier than the wide partitions. This other lemma, which really seems like what we want, is that these things are exponentially decaying in this quantity here. And the proof here, I'm not going to say is anything really magic. It's just induction. Take this formula we saw and just manipulate it for a while if you really want this fact, and you can get it out. There's nothing really exotic going on here. It would be nice to have a more combinatorial proof of this because you can kind of get some combinatorial intuition for why this might be true. But I couldn't find one, and I just had a nice algebraic proof, so I went. Question? What do you mean by compare the adjacent ones? I'm sorry. You mean with like k and k minus 1? And so the induction works by like if you could say that this is at most this quantity times d lambda minus k minus 1 over d lambda, if that's what you mean. And so that's where the induction comes from, is that you actually pick up this factor like every time you decrease k. So the corollary then, what we really want is the expectation of this. We can get something that maybe looks kind of nasty using the moment generating function for the binomial. But now we're going to use the theorem we saw before to maximize this expression. Again, this is the expression that we want. I guess I have the expectation outside here, but I could move it inside by linearity. So let's look at partitions where we're talking about polynomials with high degree when we look at their representation. Again, we saw this fact a while ago, that if the first part is small, then the corresponding representation talks about large degree polynomials. So if we're looking at large degree polynomials here, we're trying to maximize this quantity. Well, it's maximized for something very nicely just by this theorem here. We're just trying to move everything up, trying to make it as minimum noise as possible. It means we need to maximize this expression here. In this case, this quantity inside here becomes d over n, and if you use approximation, 1 minus something over n to the n, this becomes roughly exponential in minus lambda d, and this is really what we want because we have the minus d here. So this is like exponential minus lambda to the d, so this thing really is decreasing exponentially like we want. All right. Any other questions? This is step 2. What we're trying to do.
Can you go back one slide? You know how much you're losing in this first inequality? Lambda mod k versus lambda mod 2 to the k minus 1. Any feeling for this loss there?
You mean this one here?
Yeah.
I feel like you're actually losing quite a bit. It turns out, again, obviously that it doesn't matter, but I do kind of feel like, especially when k is large, that you're actually being very sloppy here. Because it kind of seems like, in the proof you get these factors of this sort of repeatedly, but it seems like you could get away with much smaller factors here. So it does seem like maybe you could tighten this quite a bit, but I don't think you'd actually get too much of a gain in the end by some of the extreme examples that we have. Good question. Any other questions? All right, so that gives us the first two things. Now, which is probably the easy part, because it doesn't require representation theory at all, is to bound the noise sensitivity. And so we're going to talk about linear threshold functions here. These are linear threshold functions. If, again, think about taking about permutations, blowing them up to their permutation matrix, blowing that up to a vector of length n squared, and then it's just a linear threshold function in the normal sense over the vectors that correspond to partitions. You can also do it this way, thinking about that it's the sign of the weighted sum of indicators of these events with some threshold. You can also do it by putting the weights into a matrix and then just directly using the permutation matrix. These are all exactly the same thing. So if you understand one, that's great.
So is this, in some sense, generalization of the standard threshold function?
Well, we're over the symmetric group, so I don't know what you would generalize, I guess.
It's the same, it's different measure, right? It's the same function. In some sense.
Does that answer your question? Okay. And so the theorem that we prove is what you get in the uniform distribution case, essentially. that if you have an LTF in this setting, this noise sensitivity is bounded very nicely. Proof here is not too long. It's actually a reduction to problems over the Boolean hypercube. Here's what we had before, and we'll remind ourselves of the noise experiment in a moment. We'll do the case where 1 over delta equals m is an integer, and so we're going to take each coordinate and stick it in a bucket with probability 1 over m, uniformly at random from these buckets. So just to make our lives easy, let's put all the buckets to be adjacent coordinates. We're going to draw sigma. And then here are our buckets, so each of these things lie in a bucket. We're going to draw a permutation that only shuffles coordinates inside each bucket so that the buckets don't trade any of their elements. Everything stays inside its bucket. So we might get something like this. It doesn't have to shuffle anything because we're just picking a uniform random permutation in each spot. So this might be our other permutation. Now I'm going to try to get a Boolean function out of this. How so? Well, the top assignments to the bucket will correspond to 0. The bottom assignments will be assigned 1. So if I give you a string in 0, 1 to the 3, then I can give you a permutation using these buckets. So if you talk about the string 0, 1, 0, we'll take this bucket, and this bucket, and this bucket. If we have 0, 0, 1, we'll take this bucket, this bucket, this bucket. So we can then define this as a Boolean function, where g of x is just the original function f, which we're assuming is an LTF, using the buckets in the natural way. I'm hiding a lot of randomness on g here. G depends on how a sigma was picked and how this down here was picked, but I'm just suppressing that for now. The key facts here that I'll have to go through quickly is that g is actually a linear threshold function in the Boolean sense, because you can just look at how the weights play here. It plays very nicely. And so no matter what g happens to be, its average influence is actually very small. The influence like we saw before when we flip one of the bits. But the other key fact is that the distribution, if we pick a random string x, and then we flip a random coordinate I, this induces what we get from the noise experiment that we want. When we pick a random x, we had a random permutation here and a random permutation here. So chunking them together gives us a uniformly random permutation overall. And when we flip one of the bits, well, that's like doing the noise, because this bucket was formed by taking coordinates random with the right probability delta. And so then sort of the one-line proof is that the noise sensitivity is just the average influence. The inside can actually always be bounded by 1 over square root of m in big O. And so this is big O square root delta. Any questions about this? And I apologize for going fast. I'm slightly over time. And so that's all 3 steps. And so if we do the same arguments that have been around since KKMS 05, once we have these 3 steps, then we can have efficient agnostic learning. But our setting here is the symmetric group, which we saw implies that we can do permutation invariant distributions. And so there's just one final slide here. I thought I had something else here, but the only LTF properties we actually use are bounded average influence, and that we're closed under some natural restrictions, like if you identify variables, you stay in the class. If you negate variables, you stay in the class. So you can actually do the same thing for, say, AC0 circuits, degree T PTFs, or any other class that's closed under this, where you can bound the average influence, and then you can learn under permutation invariant distributions in this case, with time and samples comparable to what you get in the uniform distribution case.
I was asked to make an announcement, but let's do
Okay, so other groups?
So the problem here is right, is so that we don't have any other groups on this. We used a lot of facts about the symmetric groups. We have the index for partitions here. But of course you could ask the question about many other groups. So that's wide open and interesting.
Monotone functions?
Monotone functions for this?
Yeah. Can you approximate them with low degree polynomials?
I think that you probably...
But
But they're not closed under this.
You can't do this directly, right? But if you could do this directly, like you do monotone functions like very powerfully, which would be, of course, extremely relevant. So they're not closed under negations, which doesn't make this work. But if you,
over the uniform distribution, we know you can do it with degree Boolean, right?
right?
And then
What
you
is
can
a
plug in.
monotone function?
Yeah, what is a monotone function?
In this setup, what is a monotone function?
Talking about monotone functions over the Boolean cube in the normal sense.
Oh, okay.
I guess what's weird about permutation invariant distributions is that monotone functions are kind of arbitrary, right? Because if you fix yourself to one slice, the monotonicity condition is sort of worthless, and you could have anything on a slice. So it's kind of hopeless to learn monotone functions over permutation invariant distributions because you're essentially learning arbitrary functions.
So I was asked to remind those of you who are interested that Gil Kala is going to teach a course on Boolean functions starting today at 5 or 5:10 p.m. at Soda 310. So those of you who are interested to learn about Boolean functions may want to check it.
This was true.